These are the 2.3 notes on the properties of water. So here we have a picture of the planet Earth, which is a sphere. Sorry, flat earthers. But one thing that is very obvious from looking at the Earth from space is that there is a lot of water on Earth. And this is extremely important to life. So the question might be, why are we studying water? Well, it's because water is necessary for life as we know it. Water is found in every living cell, and most cells live in some form of water. So water becomes a vital component of all the chemical processes that go on for life. Remember, we talked about that one of the characteristics of life is that life has complex chemistry. Well, much of that complex chemistry happens in solution, meaning it happens in water. Water is so important to life that when scientists are looking outside of our planet and outside of our solar system, hoping to find life somewhere else, one of the things they look for is water, specifically liquid water. So in the diagram here we have at the bottom, we have our solar system with the Sun, then Mercury and Venus, and then Earth. Earth is within a zone that we call the habitable zone. Okay, this is an area around the Sun where it is close enough, ice will melt into liquid water, but not so close that that water will evaporate away. So liquid water is very important to the presence of life. So what scientists are doing is when they're looking for life outside of our planet, one of the main factors that they're going to search for is water itself. When we look at water, we of course know that water is H2O. It is two hydrogen atoms bonded to a single oxygen atom. Now, when the hydrogen bonds with the oxygen, it bonds at an angle. And we can see that in this diagram here. Now, how scientists have measured this bonding angle gets really complicated, so we don't really need to worry about that. But every time water molecules form, that H2O, you have hydrogens on both ends and the oxygen in the middle. It forms this characteristic V shape. Remember, water forms covalent bonds, so oxygen and hydrogen are sharing electrons between the two. Water is what we call a polar molecule, because the oxygen side of the molecule is slightly negative because the nucleus of oxygen tends to draw the electrons closer to it than the nucleus of the hydrogens. So essentially the oxygen is kind of hogging all the electrons. So we get a slightly negative side on the oxygen, and then we have a slightly positive side on the hydrogens. And this is referred to as a polar molecule. The fact that water is polar is really important to how water behaves. A lot of the properties of water are going to be determined by this polar nature. Essentially, because of this slightly negative and slightly positive end, water molecules have a tendency to stick to other things. So water molecules, because of their polar, are slightly sticky in nature. And this is going to cause a lot of factors for water as we look at its characteristics. So the first question, given what you know about chemical bonding, which kind of bond would you infer would have the most interactions with polar water molecules? Would it be A, single ionic bonds, B, single covalent bonds, C, double covalent bonds, or D, double ionic bonds? The answer here is going to be A, because if a water molecule is slightly negative and slightly positive, then it's going to interact with bonds that have charges. So those would be ionic bonds. Now, why isn't it D? Well, because there is no such thing as a double ionic bond. Double bonds only occur in covalent bonds. So an ionic bond is going to interact with water molecules. There are several properties of water that are really important to life. There are 5 major characteristics that affect life from the cellular level all the way up to the ecosystem level. And we're going to look at those properties one by one. So the first property is that of cohesion and adhesion. And this is in reference to the sort of stickiness that water molecules have. Cohesion is water's tendency to stick to other water molecules. So water molecules have a tendency to stick together. The slightly negative side and the slightly positive side tend to draw into each other, and they tend to stick. Because of this cohesion, at the surface of water, you have a very strong bond amongst those water molecules. This is what we call surface tension. So in the example that we have here, we have an insect standing on top of the water. The reason why some insects can do this is because the surface tension is strong enough to hold up that insect despite the forces of gravity trying to pull the insect through. So essentially, the bond between those water molecules is going to be stronger than the force of gravity. The other characteristic we have here is adhesion. Adhesion is where water molecules have a tendency to stick to other molecules other than water. So looking at the diagram here in the bottom, we have a graduated cylinder. And you'll notice every time you put water in a graduated cylinder, there's a little bubble that forms at the top. Okay, that bubble is as a result of the adhesion of water molecules sticking to the side of that graduated cylinder. And that bubble is very characteristic. It's what is known as the meniscus. Now, if you combine cohesion with adhesion, you get a quality called capillary action. And capillary action is the tendency of water to move upwards against the force of gravity. You can illustrate capillary action with a piece of paper towel. So if you take a piece of paper towel and dip one end into some water, you'll notice that the water starts getting sucked up into the paper towel. This is the result of capillary action. The water molecules are sticking to the particles of the paper towel, and then that draws more water molecules up the paper towel due to cohesion. Now, this principle of capillary action is extremely important to life because this is how water gets to the very tops of trees. Plants have roots. These roots dig into the soil, and these roots are what helps plants absorb water from the ground. So when it rains, water gets absorbed into the soil, and those plants absorb that water through their roots. But how do we get that water up from the roots all the way to the top of the plant, especially when we're talking about a tree that could be literally hundreds of feet high? Well, this is the result of capillary action. So inside of plants, you have tiny vessels that are called vascular tissue. And the water seeps up this vascular tissue due to cohesion. Water molecules are sticking to the side of these tiny little tubes flowing up the trunk of the tree. As water moves up that tube, it pulls more water molecules up with it. So imagine you have a string with beads, and you pull that string through a straw. As you pull one bead out the top, it's going to pull more beads up through the bottom. So this is what's happening inside of a plant, is as water is being pulled up through the length of the vascular tissue, more water is being drawn up. Now that water is being drawn up through the plant by molecules of water evaporating out the top of the plant. So at the leaves, you have pores, which are called stomata, and the water molecules are evaporating out the top, and that's pulling that chain of water molecules up through it. This is a process known as transpiration. This is extremely important to how plants are able to get water throughout their entire bodies. If you go to some place like the Amazon rainforest in South America, so much water is transpired through all the trees that are in the rainforest that by midday there are clouds at the top of these trees. These clouds are being produced by the evaporation of water out of the trees themselves. So literally the trees are making clouds. The next important property of water is that water is an extremely good solvent. It's often described as a universal solvent. Now, what we mean by a solvent is that this is a substance that can break down other substances. So if you put salt in water, that salt breaks down. Water is a polar molecule. Because of the slightly positive and slightly negative ends of that water molecule, we can pull positive and negative ions apart. So when we put salt into water, those ions are being pulled to pieces. That's why the salt dissolves. In a solution, we have solvents and solutes. The solvent is the liquid, in this case water. The solute is the substance that we're breaking down. So salt would be the solute in a saltwater solution. Now, when you mix sugar into water, sugar also dissolves. But sugar is not an ionic compound. Sugar is actually a polar molecule. And since it is polar, it has a slightly positive and a slightly negative side as well. So water can work its action on that also. When you have ionic compounds or polar substances, they easily break down in water. And this is what we call a hydrophilic substance. So salt and sugar are very good examples of hydrophilic. The term hydro, of course, means water, and philic comes from the word philia, which means to love. So hydrophilic means water-loving. Substances that are nonpolar are not likely to break down in water, and we describe these as hydrophobic. The term phobic comes from the word phobia, which means to hate or to fear something. So hydrophobic means water-fearing or water-hating. Non-polar substances like oil will not break down in water. So famously, if you put vegetable oil in water, the oil just kind of bubbles up to the top of the water. It will not break down, it will not dissolve in water. So sometimes water is referred to as the universal solvent because it can break down a lot of things, but that's kind of misleading because water can't break down everything. Only ionic substances and polar substances break down easily in water. So another question. In the picture below, a drop of dew is suspended on the surface of a leaf. The material of the leaf is likely to be A, hydrophobic, or B, hydrophilic. The next property of water, which is really important, is that water has a lower density as a solid. So normally, when you have substances, they can be in 3 different phases: solid, liquid, or gas. So as you have a liquid and you start cooling it down, it is going to become solid. So if I have liquid iron, molten iron, and you cool it down, it's going to become solid iron. Generally speaking, when substances cool down, their particles, their atoms, their molecules get closer and closer and closer together, and that's what makes it solid. Water, however, is slightly different. Because of the cohesion of those water molecules, when the water molecules come together, they start sticking together. So as we start cooling down water, eventually the water molecules are going to start arranging themselves into a very particular pattern, and it actually forces the water molecules apart. So water is actually most dense at about 4 degrees Celsius. That's just slightly above freezing temperature, because that's as cold as water can get, and the water molecules get closer and closer and closer together until those hydrogen bonds, the forces that are sticking those water molecules together, start forcing them apart, and it actually makes them less dense. So solid water is actually less dense than liquid water. Now this has some really important consequences. First of all, ice floats. So if you put ice into water, it's going to float to the top, because substances that are less dense tend to rise and tend to float. So that means ice floats on top of the water. So if you have an iceberg, like pictured here on the left, that iceberg is going to be floating in the ocean. It's not going to sink down to the bottom. Related to that, when water freezes, it freezes from the top down. What this means is that a layer of ice can form at the top of a lake, and you have still liquid water beneath it. So when a lake freezes over, the fish that are living in the lake can actually still continue to swim around in the water below it. Fish that live in environments where the lake is likely to freeze often have adaptations that allow them to survive in this very, very cold water. Another property that comes from the expanding nature of water when it freezes is that when water gets into cracks and freezes, it expands and it can actually break things apart. This is a strong force of erosion in nature. In the example here on the left, if water gets into the cracks within a rock and then freezes and expands, it can actually provide enough force to crack these rocks apart. Entire mountains can be broken down into tiny little rocks, tiny little pebbles, through the force of water freezing and expanding. This brings up an interesting question when looking at water elsewhere in our solar system. Europa, one of the moons of Jupiter, is covered in sheets of ice, and it is theorized that below these very thick sheets of ice, there is actually liquid water underneath. How can it be liquid water underneath? Well, Jupiter as a planet actually radiates quite a bit of heat energy, but outer space is very cold. So the outer layers of the liquid water on the surface of Europa are frozen solid, but there's enough energy coming off of Jupiter to actually warm the waters underneath. Now, how do we know there's liquid water on Europa? Because when we observe the surface of Europa, we actually see ice volcanoes. That is, water from underneath the surface gets pushed up and spout out of the ice sheets as these geysers. Okay? And when the water hits the cold vacuum of space, it immediately freezes and snows back down. So this is kind of an interesting scenario because wherever you have liquid water, there is the possibility of life. So scientists are actually hopeful that someday we can get a rover or even people to the surface of Europa and check to see what's going on beneath its surface. Now, one would think, okay, we'll just drill down into that ice and then see if there's any living things down there. Well, that's kind of a tough job because even though it's ice, it's super cold, so it's as hard as concrete, and it's several hundreds of miles thick. So to drill down that deep is nearly impossible. But we can still look for life in this water underneath because that water periodically gets shot up into the air through these ice geysers. So what a rover could do is it could go over to one of these ice geysers and scoop up some of the snow samples that are around and check to see if there are microorganisms in there. And if there are microorganisms, then quite possibly there could be bigger organisms lurking underneath the surface of Europa. It's a really exciting idea, but we really don't have any way of proving this hypothesis right now. Another really important property of water is that water has a high specific heat. Now, what this means is that water can absorb a tremendous amount of energy before it increases in temperature. This is what we call water's heat capacity. So imagine you have a pot of water and you stick it on a stove. When you turn on the stove, the water doesn't immediately start boiling. It takes a while for that water to heat up enough to start boiling. That's because the water starts to absorb the energy from the stove and eventually starts increasing in temperature. As it increases in temperature, the water molecules start to move around and eventually will start boiling and start evaporating into gas. So water has this high specific heat, which means it takes a while to heat up water. It also takes a while for water to cool back down. This high specific heat plays a very important role in how living things can actually manage their temperature. And we have what is known as evaporative cooling. And in Florida, we're pretty familiar with this. When it's hot outside, you start to sweat. As you sweat, you're releasing water. Now that water is eventually going to evaporate off of your skin. As it evaporates, it essentially sucks heat away from your body, and this allows your body to cool down. This is the way that your body can regulate its temperature. Now, there's only so much that you can sweat, so you can only evaporate so much water before your body's temperature starts to increase. That's why on really hot days, you still have the opportunity of getting overheated and having something like heat stroke. The other danger of this evaporative cooling is you could lose too much water and end up dehydrating. Now, if you look at other animals like dogs can't sweat through their skin because they're covered in fur. So instead, dogs will pant, meaning they open their mouth and they release water vapor through their mouth and through their nose, and this gives them the same advantage of evaporative cooling. The high specific heat of water also plays a very important role in moderating the Earth's temperature. The Earth occupies what we could refer to as the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And having so much water on the surface of the Earth helps with that because 70% of the Earth's surface is covered in ocean. And as the ocean absorbs the energy from the sun, it releases that energy back slowly. During the summer, the sun is heating up the oceans. And during the winter, the oceans basically release that heat and warm the Earth. Without this much water on the surface of the Earth, summers would be a lot hotter and winters would be a lot colder. So because we have so much water that acts as this heat sink, it moderates the temperature on Earth and makes it livable. Okay? If the Earth was too hot or the Earth was too cold, life on this planet wouldn't be able to exist. So the next question, what would be the possible consequence if water had a low specific heat? A, water would boil at a much higher temperature. B, humans would sweat a lot less. C, the temperature changes on Earth would be more dramatic. Or D, water would be more adhesive to surfaces. The final characteristic of water that we need to pay attention to is the ionization of water. Water is H2O, but water can actually split apart, and this will give us ions. Remember, ions are charged atoms. So if you have H2O, we can actually break off one of those hydrogens and have a hydrogen ion, which has a positive charge. And then what's left is an OH, that is the remaining hydrogen and remaining oxygen. This has a negative charge, which we call a hydroxide ion. Substances that produce hydrogen ions are what we call acids. Substances that produce hydroxide ions are what we call bases. We measure the acidity or the basicness of a substance on what is called the pH scale. pH stands for potential hydrogen. So this scale goes from 1 to 14, and in the middle is 7, which is neutral. So pure water, that is water without anything in it, has a neutral pH. The amount of hydrogen and the amount of hydroxide is basically balanced. Whenever we add a substance that causes more hydrogen ions than hydroxide ions, we call that an acid, and the pH starts to lower. If you look at this chart, things like tomato juice, 7-Up, Coke, these are acidic. Vinegar, which is also known as acetic acid, these are things that produce hydrogen ions. And then anything that produces hydroxide ions, that is the OH minus, that goes up on the pH scale. So anything 8 to 14 is going to be a base. Okay, so things like baking soda, things like toothpaste, detergents, these are going to be bases. Really strong acids and really strong bases can actually break things down. Acids have a tendency to react with metals. Bases have a tendency to react with organic tissue. So if you get a strong acid on your skin and a strong base on your skin, the base is actually going to cause a much worse chemical burn. There are quite a few household chemicals that are acidic and that are basic. And this is something that you have to pay attention to when you're using these substances like cleaners and detergents around the house. So the final question, which property of water best explains the fact that ice fishing is possible? Ice fishing, if you're not familiar, because we live in Florida, is where you go out to a frozen lake, you drill a hole in that lake, and then you cast your fishing pole into that hole to catch the fish that are swimming around underneath that ice. So how is that possible? Is this due to A, the cohesion, B, the universal solvent, C, the low density as a solid, D, the high specific heat, or E, the ionization and pH? This is the last of the notes for Unit 2A. We went through a lot of information this week, so make sure that you go back through your notes and review to make sure that you understand everything that we've talked about.